Hi everyone, welcome to channel. So today we are going to discuss the topic about Nvidia switches. Why do we need Nvidia switches and what is the concept of RoCE? So if you see this diagram, you might have understood by now. So without RoCE, the server CPU utilization will be high, and with RoCE, the server CPU utilization will be low because every packet is bypassed. Okay, so I'll explain this a little bit more. So if you see here, so let's assume, let me change my color pen. Let me partition this. And this is server 1. This is server 2. I mean, this entire thing comes to server 2 and this entire thing comes to server 1. So now when server 1 is communicating to server 2, so what are the packets it's sending? So it has to pass the server CPU first, and then it has to process it. It has to process it, and then it has to send to the NIC. And here we will be having a switch, network switch. So these packets are passed to the switch, and switch further passes this packet to the server 2 network interface card, and from this network interface card the packet goes to the server CPU. Here server CPU has to process the packet and then pass to the user, I mean the application layer. So here what is happening, every packet is being processed by the CPU on both the sides, server 1 and server 2. With this, the server CPU is utilizing more, and which causing the more burden to the CPU here. So what Nvidia brought here, so on Nvidia what they'll do, they will insert a GPU here. Here they'll insert a GPU, which is called a graphical processing unit. So whatever the packet comes, it hits this GPU, and this GPU will directly passes the information to the network information card, and from there to switch, and from switch to NIC, and again NIC to this GPU, and from GPU to application layer. So nowhere the CPU is involved here. If you see here on the right hand side, let me change my pen color. So if you see here, whatever the packet is coming, it is not involving the CPU, it is directly bypassing the CPU and going to the NIC. Similarly, here we will be having a switch, network switch, and this switch passes this packet to the NIC, and NIC to the, it bypasses the CPU and directly passes to the application layer. So with RoCE, it bypasses CPU. So whatever, I mean the offload, so whatever the overhead here the CPU has, we are offloading it. So when we are offloading it, the CPU is intended to do some applications, right? So primary applications. So now CPU is free to do those application works. Okay, so now whatever the request comes, the GPU will take care here. GPU is graphical processing unit. Okay, let me show you one more scenario. So it explains you more. So if you see here, without RoCE, the packet passes each and every application layer, socket, transport, NIC, driver, and then it comes to NIC, and from NIC to switch to NIC, again it passes all the layers. But with RoCE, if you see on the right side, from application to application, it going directly. No layers are involved here. That is the advantage. Okay, so that is the advantage of. So here two things are needed here. I mean we need to configure the switch side as well as server side. So first let me tell you few things which are mandatory to know about this concept. So one is, first thing you should know is RoCE. So what is RoCE? R stands for RDMA. RDMA over converged Ethernet. So what is this RDMA? Remote direct memory access. Remote direct memory access over converged Ethernet. So what is this RDMA here? So what does it do is, it allows devices to perform direct memory to memory transfers. As you see in the previous image, application to application, it is directly communicating, right? So it allows devices to perform memory to memory transfers at the application level without involving the host CPU. Okay, so with this process, it enables lower latency, higher throughput, and better performance. And also you should know about few more things, which is PFC, okay, which is priority flow control, and next ECN, which is explicit congestion notification. So you should also know about these two things, priority flow control and explicit congestion notification. So let me explain you. So let's say we have a server 1 here, which is connecting to switch 1. Switch 1 is in turn connecting to switch 2. Switch 2 connecting to switch 3, and switch 3 is connecting to server 2. So when communicating from server 1 to server 2, we have in between switch 1, switch 2 and switch 3. So this ECN is what we said, explicit congestion notification. So it means it is not an algorithm, it just sends a notification messages. So when server 1 send a packet to switch 1, switch 1 now further forwards the packet to switch 2. Now switch 2 is already in congestion. So what this switch 2 will do is, it enables or it marks the ECN on the TCP/IP packet and forwards to switch 3. Switch 3 sees the ECN enabled on the TCP/IP packet. It understands that switch 2 is having some congestion issues. So this information is also forwarded to server. So when server is acknowledging back, okay, so it also does the same thing. When it is acknowledging back, it has the same mark, ECN mark, in the acknowledge packet, and it forwards, and this acknowledgement is forwarded back to server 1. So now here the server understands that in between the switch 2 is facing some issues with the congestions. So now it slows down the packets. So this is the ECN. ECN means end to end, whatever the devices are in between, the notification messages are sent. PFC is a priority flow control which enables between peer to peer. Let's say we have switch 1 and we have switch 2. Okay, we have communication. So PFC is enabled here and PFC is enabled here. So that's how it's a peer to peer. Or we can see one more thing. Switch 1, it is server 1 and this is server 2. So here and here and this point and this point, we enable PFC. So PFC is peer to peer, ECN is end to end. Okay, so if you understand these steps, I will forward for the next configuration steps. ECN is nothing but it's a congestion notification, or we can say congestion signaling algorithm. Okay, it informs the sender about congestion so that respective measures can be taken to avoid this. Okay, so let me erase this and I'll go forward. So now to configure in the Nvidia switches, okay, we should have a DCB priority flow control enabled first. So we can do it on globally or on the interface wise. So we should use DCB priority flow control enable. So when we do this, it asks for confirmation. So just press S and then it goes to the next thing. Okay, it asks for the yes, and next you do the priority. So we already enabled priority flow control. Now give the priority. Which priority we should give? So again, DCB. I'm just writing in a short form. PFC. It's a priority flow control. Priority 3 enable. Okay, and we should go to the interface Ethernet. Let's say we have 1/1 and 1/2. Okay, and again DCB priority flow control mode on force. So if you don't give this on force, by default if you enable this, it asks to shut down the interfaces. So if you give this mode on, without shutting down the interfaces, we can do the configuration. Once it is done, you can use the command show DCB priority flow control. So output of show DCB priority flow control shows which interfaces are enabled for the PFC. Okay, so now what we should do after this, we should do the configuration on the server side as well. We should, on the server side also the PFC should be configured. So once the PFC is configured on the server side, you should run the RoCE traffic, the RoCE traffic from server 1 to server 2. In between we have this switch. Okay, so now once the RoCE traffic is run between these servers, we should check by using the command show interface Ethernet 1/1 counters priority 3. Okay, so when we issue this command, usually what we'll see the information of RX and TX side information. So how many broadcasts, how many messages, what are the if there are any errors. Okay, so all this information on both RX and TX information we'll see. If you run this command, especially show interface Ethernet 1/1 counters priority 3, then you will see that if you see any packets incrementing on pause frames or packets, if you see any incremental counters on the pause frames or packets on the RX or TX side, it means that whatever we configured, which meant the PFC is functioning as intended. So what is this pause meaning? So let's say we have a switch here, switch 1, and we have a server here, server 1. So when and we have a server 2 here. When there is a communication between server 1 to server 2, it communicates from switch 1 to server 2, right? So when the packets are coming from switch 1, here it sees it's already in congestion, okay, and this PFC is enabled on the switch and on the server side. So it says hold on, the server 2 says hold on, I'm already in congestion. Then this information is passed from the switch 1 to server 1. So server 1 holds, it pauses the packets. Okay, so those packets can be seen on the switch interface, meaning the packets are not dropped, it just paused for a while, and once this congestion is cleared, S2 sends again a message that I'm ready. Then those packets are passed to the S2. Okay, that's how we can see in the lossless networks. So the main intention is to the lossless networks. And on the server side, the CPU is not involved. So that's the advantage of this RoCE. I hope I have cleared, and if you have any queries, you can visit this video again, and if you still have any queries, you can comment me. I'll reply you. Thank you so much. Thank you for watching.